Hello, welcome. We are in Unit 9, and in this lesson, we're going to look at some really interesting properties of logarithms. We've started with some of the basics of how to convert between exponential form and logarithmic form. So here we're going to start taking a look at some properties like the multiplication property, the division property, and the power property, which will eventually help us solve equations with logarithms. To start, let's just review what is a logarithm and how do we convert back and forth between logarithmic form and exponential form. So if we remember, a logarithm is a rearranged form of an exponential equation or an exponential function. So we're converting between exponential functions and logarithmic functions. And we know that logarithms help us solve exponential functions. We have learned that logarithmic form looks like this, where we have a base, an answer, and that's equal to our exponent, which correlates. If I do the base and the exponent, that should get us to the answer. So we see that all of these pieces are the same. They're just arranged differently between the different forms. Now, the first thing we're going to look at is two very special types of logs. One of these is called a common log, and the other is called a natural log. And both of these are very common logarithms that we use that will help us as we're solving equations with logarithms. So a common log is any logarithm that has a base 10. So a common log will always have a base 10. So in logarithmic form, that means the number that would go in place of b would be 10 anytime we have a common log. So if we see something like this, if we have the log of a equals x, we typically just won't write that 10. Anytime we don't write a base, it's considered to be a common log, which means the base is 10. And so if I were to convert this into exponential form, we know that the base is 10, even though it's not written. Kind of like when we have a square root, but we don't write the 2 out in front because we know it's a square root. Same thing here, we just don't write this 10. And so really, if we were to convert into exponential form, this would be, our base would be 10. We would have our exponent, which would be x, and that would equal our answer, which is a. So we just know if there's not a log written, if there's not a base written, we know that's a base 10. Similarly, a natural log is another common type of logarithm, and this is any logarithm with base e. Base e. We learned about e when we talked about continuous growth and decay. E is a number. E is approximately 2.71828. And we use this in a similar way that we use our common log. However, we don't use the abbreviation log, so we don't use log. With a natural log, we'll use the abbreviation ln. So the n is kind of where the natural comes from. This is an L, not a 1 or an I, so it's a lowercase ln. And if we have that a equals x, again, we're assuming this is base e. So anytime it's not written, we're going to assume that's base e if we see this ln. So this will be e to some power of x equals a. We can see both of these actually show up on our calculator. So if you take a look at your calculator, over on the left-hand side near kind of the top of the number pad, you should see a button for log, and we should see a button for natural log. So log is our base 10. You can even see that little 10x above it helps kind of remind you that it's base 10, whereas our natural log has a base e. So again, kind of reminds us that that's base e. So if you're going to type your natural log on your calculator, we'll use ln. All right, before we talk about our properties of logs, we're going to go ahead and just evaluate some logs on our calculator here. So we're going to estimate to the nearest hundredth, which would be 2 decimal places. So to type any logarithm on a calculator, I'm just going to go ahead and type in, notice there's not a base here, so this is base 10. So I'm going to go ahead and use my log key, which is here, so I'll press log, and then we can just enter that number. So I'll just type in the log of 100, and that would be 2. We can do the same thing here. So I'm going to hit the log button and type in 0.001. and that's going to be -3. And then here we have some ln's. So again, your ln button is right below your log button, so kind of next to the 4 there. So I'm going to go ahead and hit the natural log, and we can type in 16. We're going to round to the nearest hundredth, so I'll say that's about 2.77. And then the last one, the natural log of 1. So again, I'll hit that ln button and type in 1. And that's going to give me 0. So we can evaluate these on our calculator, and this will be really important when we actually start solving, is being able to type these on our calculator. Note that we can only type in log with base 10 or log with base e, so a natural log. Those are the only 2 options. We can't really type in other bases. So we'll actually talk about that in a different lesson. Let's go ahead and move on to some important properties of logs. These 3 properties are going to help us as we simplify logarithms and as we start to solve equations that have logarithms. So the first property is our multiplication property. This relates multiplication to addition. So we're going to define this just in symbols, but then we'll take a look at some examples of what this could look like. So let's say we have a log with some base of b, and we're taking that log of 2 things that we're multiplying. So let's say we're multiplying x times y. We can do something called expanding. We can expand this x times y, and instead of doing 1 log with multiplication, we can separate this into 2 logs that we're adding. Note that the base will stay the same, so I'm going to take the log of that same base of x and we'll add it to the log with that same base of y. So we see this correlation between multiplication and addition, and we can do the reverse. If I'm given 2 logs with the same base that we're adding together, to simplify, we could actually just multiply those 2 things. So multiplication relates to addition, division will relate to subtraction. So again, let's say we have a log with some base of b and we're dividing 2 things. So let's say I'm doing x divided by y. Again, we could expand and separate those. Note that the base will still stay the same. So I'll take the log with that same base of x and we'll subtract the log with that same base of y. So we see that division correlates with subtraction. Once again, if we start with something with subtraction, we could do the reverse and change that into addition. And then the third property is our power property, which relates taking a power to multiplication. So let's say we have the log of some base b, and we're doing x to some power of y. What we can do is we can actually bring this exponent down in front and multiply by that value. So that's actually going to be y times the log base b of x. So anytime we have this exponent, we could go ahead and bring that out in front and change that to multiplication. And again, vice versa, if we're multiplying something times a log, we could change that multiplication into an exponent. So on the next page, we'll go ahead and actually take a look at some of these properties. The first thing that we're going to take a look at is simplifying logarithms. So to simplify means to make them into one logarithm. So my goal in simplifying here is to get a single logarithm at the end. So here we note we have the same basis, so a 5 and a 5, and I see that we're adding. And if we remember, addition correlates with multiplication, so this multiplicative property. I'm going to go ahead and combine these into one logarithm. So when I do this, we can keep the log, we'll keep the base the same, the base never changes, and we'll go ahead and do 3 times x. So instead of adding a log of 3 and a log of x, we can just do 3 times x, and this would be the single logarithm we get as the answer. All right, let's try another one. Here I notice we have subtraction, and subtraction will correlate with division. However, I also see we have this number out in front, this 4, and this is actually multiplication. So first I'm going to use this power property, where we take that multiplication, and I'm going to go ahead and turn that into an exponent. So this 4 I'm going to kind of put above this 3, so I'm going to change this into log 2 of 3 to the 4th power. Minus log base 2 of 3. Now we have this 3 to the 4th power, which we could actually solve here. So I'm going to go ahead and actually do that. 3 to the 4th power is 81. All right, and my last step to simplify will be to do this subtraction. Now this subtraction we're going to change into division. So instead of subtracting these numbers, I'm actually going to divide these numbers. So this is going to give me the log. Again, my base never changes as we go through this process, and I'll do 81 divided by 3. We could simplify this again because these are numbers. I could go ahead and do 81 divided by 3. If we do that, that's 27. So this whole thing is the log base 2 of 27 would be my final answer. So as much as you can simplify, we do want to simplify throughout this process. Let's go ahead and try one with just variables where we can't exactly simplify. Again, whenever we have this number out in front, that will be our power property. So we can go ahead and turn this 3 and this 2 into an exponent. So I'm going to change this into the log of x cubed, and I'll change this into the log of y squared. We'll keep this minus log z. And here I see addition, which we could simplify into multiplication. Here I see subtraction, which we could simplify into division. So we're going to actually combine both of those together. So I'm just going to keep, again, all these logs have the same base, so I'll keep that log. We can go ahead and multiply. So I can do x cubed times y squared. And then we'll go ahead and divide by that z. So this is kind of what we end up with here when we combine both multiplication and division. All right, and last one, here we just have a natural log. It doesn't change at all. All of these properties still apply to natural logs. So again, I'll do that power property first to make these into exponents. So I'll get the natural log of x to the 4th and the natural log of 3 to the 5th. Once again, anytime we actually have a number to that exponent, we want to go ahead and simplify this. So I know 3 to the 5th is 243. So I'll do the natural log of 243. All right, last step, we're adding here. So to combine with adding, we'll go ahead and multiply. That's going to give me the natural log. I'll multiply these, and I'm just going to write the 243 out in front, since that's typically how we would do so. So I'm going to do 243 times x to the 4th. We're taking the natural log of that. That's as simple as we can get it, and we're done. The next set of examples is actually doing the reverse of this. So rather than simplifying and combining logarithms, we're now going to expand, which means to write it as multiple logarithms. So anytime we see multiplication, we'll change that to addition. Anytime we see division, we'll change that to subtraction. Anytime we have a power, we'll bring that down out in front as multiplication. So first, if I were to think about this, this is 5 times m, and since we're multiplying, we could change that into addition. So I'm going to get 1 log with the 5. So again, we'll keep that base 4, and I'll add it to another log with the m. Notice that your base stays the same. The base never really changes throughout this entire process. So we're just expanding. We changed that multiplication into addition. Here, I note 2 operations. One is multiplication, so I'm doing 16 times x squared. And then we also have this exponent. I'm actually going to undo that multiplication first. So I'll go ahead and do the log of 16. Again, my base will stay 2, and we'll add that to the log base 2 of x squared. So I'm separating that 16 and x squared. Then I do go ahead and simplify this exponent. I don't want any exponent, so I'm going to go ahead and bring that down out in front as if it were multiplication. So I'll do x times the log base 2 of x. Sorry, this should be a 2, not an x, because we're bringing down that exponent of 2. So this should be 2 times the log of x squared. All right, number 11, there's a lot going on here. I kind of see 4 separate things. This would be 3 times x squared times y cubed divided by z squared. So we have multiplication, multiplication, and division, as well as some exponents. So the first thing I'm going to do is separate all of this multiplication and division. So I'll do the natural log of 3. We were multiplying that by x squared, so I'll add that to x squared. We were multiplying that by y cubed, so I'll add that to y cubed. And then we were dividing by z squared, so I'll go ahead and subtract that since we were dividing. So this is multiplication and division. Again, we don't want any exponents, so I'm going to go ahead and bring all of these exponents down out in front as multiplication. So we'll keep that natural log of 3. I'll go ahead and get 2 times the natural log of x, and 3 times the natural log of y, and minus 2 times the natural log of z. This would be fully expanded when we no longer have any multiplication or division or exponents. All right, and then we have our last one here. And this last one, we see we have this 2 on the outside. So here we also have division. Now, because this 2 is outside of the parentheses, we do want to be careful of this. The first thing I'm actually going to do is distribute this 2 to both things in the parentheses. So I could actually think of this as the log of x squared over the log of 3 squared. And I do want to be careful of that. So that can be a little bit different than maybe some of the exponents in the other one. And this 3 squared, I'm going to go ahead and actually simplify to 9. So I'm going to think of this as the log of x squared over 9. So as we simplify, really there will be 2 things that I pull out. One will be this x squared, one will be the 9. Since we're dividing, we can change that into subtraction. So I'll do the log of x squared minus the log of 9. And really the only thing left is to bring this exponent down in front. So this will be 2 times the log of x minus the log of 9. And that's fully expanded. All right, and the last thing to briefly touch on is some unique cases when we look at natural logs as well as common logs. Is just what happens when we have kind of some of these unique cases. So here, if I have the log base 5 of 5, really what we're thinking about is this is 5 to some power is 5, which we know would just be 1. So anytime our base and our answer are the same, that's always equal to 1. Therefore, we know the natural log of e. I know this is a base e. So again, this is e to what power is e? Again, that would be 1 because the base and the exponent are the same. Here, my answer is 1. So this is b to some power is 1. And if you guys remember from Unit 7 when we studied exponents, we know anything to the 0 power is 1. So anytime your answer is 1, this number here is 1, we know that that's going to be 0. Again, this will be 0 because this is e to some power is 1, and anything to the 0 power is 1. And then the last one is what happens if this is 0. So this is b to what power is 0, which we actually can't do. We will never get 0, even if we do a 0 power, because a 0 power actually gets us 1. So this is actually no solutions. This is undefined. We cannot solve this. Similarly, if we have a negative, this is 10 to what power is negative 2. We actually can't do that either. So we'll never get a negative answer when we're doing exponents. So this is actually also undefined. And those are just some unique instances. We'll use those when we start solving some logarithms as well.